Alrighty, folks. Today we'll be talking about section 3.4, which is circling back around to that topic that we started off the semester with, which is rate of change, right? And if we recall from what we talked about then, right, the limit as x goes towards x naught of f of x minus f of x naught all over x minus x naught is what we said the instantaneous, there we go, I think I spelled that right, rate of change at x naught is, and now we know that that's exactly the derivative at x naught. So sort of circling back around and connecting up what we did at the start with this new definition that we have. And then basically it goes into a bunch of different types of word problems that we can have. Right, so one that it sets up for us is the idea of marginal cost. So marginal cost is the cost it takes to make one more. Right, so if C is a cost function, then the marginal cost is how much it takes to make that x naught in first, right? So if the marginal cost at 50 is going to be the cost it takes to make that 50 first, and so it's going to be how many does it take to make 51 total, and we subtract from that how much it took to make the first 50, and we get exactly how much it would take to make just that 51st one. So that's our idea for marginal cost. And the way this connects with calculus is we can estimate it, right? We can't find the marginal cost, but we can estimate it by knowing that this is close to the derivative at x naught. All right, one of the things we got in a previous chapter, just to sort of remind us, is that the limit as x goes to x naught of f of x minus f of x naught all over x. Whoops, let me write this. This one works better with h. I forgot that when I started, but limit as h goes to 0 of f of x plus h minus f of x over h. That equals f prime of x, right? And what that means is that f prime of x is close, right? Squiggly equal sign means that it's close to, but not quite exactly equal, if h is small. Right? And if we think about what it means to put this in terms of our cost function, this, again, thought bubble, is like saying h is equal to 1. Right? Because if we're dividing by h and h is equal to 1, that doesn't actually change anything. If we are, here we have x naught plus 1, and here we have f of x plus h, so that's another indication that h should be 1. So this marginal cost formula is a lot like the difference quotient, but with h specifically being 1. And now 1's not the most small number. It's still a pretty small number, right? So in some cases, and usually in cases like this, where when you're trying to find the cost of something, usually you're talking about whole numbers. So the difference between two numbers is rarely less than 1, right? So sometimes this is small enough. Sometimes. And in this case, it tends to work out. So another application we have is if S of t is a position function, right? So in other words, S of t equals where something is at time t, right? So S of 5 would be where something is after 5 minutes have passed, say. So if that's the case, then the derivative of S actually has a special name. It's called v of t, and this is the velocity of the moving thing at time t. Right? An instantaneous velocity, not average velocity. Right? And we also have that the absolute value of velocity is the speed. Right? So velocity can be negative or positive. Negative means that it's slowing down. Positive means that it's speeding up. Or rather, what direction it's going. Sorry, not slowing down and speeding up. But it tells us what direction it's going. But the absolute value tells us how fast it's doing that. So a sort of subcategory of this is motion under the influence of gravity. So this is going to be a type of position function, right? It's generally going to measure how far off the ground something is, right? And the formula we have for it is S naught plus V naught times T minus 1/2 GT squared, where S of T equals how high at time T. S naught equals how high at the start. Right, so we could have also wrote it as S of 0. V naught equals velocity at the start. And G equals gravity, which for our purposes we can use 9.8 if we're talking about meters per second squared, or we're going to use 32 if we're talking about feet per second squared. So if we have this, right, this is our setup. This is the standard model, or a standard model for motion under the influence of gravity. And when we have that, the velocity at time t is going to be, we need to take the derivative, right? This is the derivative of s, right? So if we take the derivative of s naught, that's just a constant, so it becomes 0. This is a linear term in a polynomial, so we just get the coefficient. And for this one, we have to bring that 2 down and multiply it by the 1/2. So we just get 1 out of that. GT, and then we make this 2 and we make it go down by 1 to get a power of 1. And so we just have V naught minus GT. Right? So there's all sorts of other word problems that you can do. Really anything where you're talking about a rate of change, you're probably going to involve the derivative somewhere. So we're just going to hop into some problems. So problem 1, let capital T of t be the temperature in degrees Celsius at time t in minutes. Oops. For 0 less than t less than 20. Given by t of t is equal to 5/7 t squared minus 12t plus 150. So how fast is it cooling or heating at t equals 14? So, yikes, sorry about that. I will make sure we don't get interrupted by that again. All right. So, this question of how fast is it changing, right? We have a special word for it because it's temperature, but asking if the temperature is cooling or heating, or if something is cooling or heating, is asking how the temperature is changing, right? So how fast tells us it's a rate problem, right? Cooling or heating says that it's a change problem. So this is a rate of change problem, and our first inclination should be to find the derivative, because the derivative is the rate of change. So we want to find t prime of t, right? And this is, again, a polynomial, so we're going to get to use our power rule a whole lot. We get to take this square and bring it out front, so we get 10/7 as the coefficient, and then the 2 power becomes a 1 power. Next one is linear, so we just have to take the coefficient, and then the last one's a constant, so it just goes away. Right? So our rate of change function is 10/7 t minus 12, and then the question asks specifically what if little t is 14. Then we have 10 times 7 times 14 minus 12. So this is going to be the 14 and the 7 cancel, and that leaves a 2 up top, so 20 minus 12. So we get 8. Right? And so one thing this question didn't explicitly ask, but something like this might very well ask it, which is this heating or cooling, right? And we can tell that by the rate of change, right? Because if you're changing by +8, that means you're getting bigger. If you're changing by -8, that means you're getting smaller. So since this is changing by +8, that means that the temperature at that time is heating by 8 degrees. Right? Alrighty. So our next problem, we're going to say an object's position is given by s of t equals 3t to the 4th minus 24t squared kilometers at time t in hours. And then we want to answer when is the object instantaneously motionless. And what is the object's speed at 1 hour? Right, so to go with the first question here, question A, right? Instantaneously is sort of a good word to start trying looking for the derivative as well. Rate of change is the more clear word, but instantaneous is something that tends to come up when we're looking at the derivative, right? But the key thing here is motionless, because motion is the rate of change relative to position, right? So the answer to the question, or a way to rephrase question A, is at what t is the rate of change of the position equal to 0? So when is there no motion? When is velocity 0? Right? So that's one of the things we can be looking out for to give us that hint that this is a derivative problem. Right? So first we need to find s prime of t. Right? And again, this is another polynomial, so we get to use the power rule a lot. Right? First we're going to take this 4 and we're going to bring it down here. Then we're going to take that 4 and we're going to go down by 1. So we get 12t cubed. Over here, we've done a lot of squares. We're going to keep doing that. We're going to bring the 2 down and multiply it out. Then we're going to make the 2 go down to 1. So this is our velocity, right? And that's the thing that we want to know, when is it equal to 0? So we've got 12t cubed minus 48t equals 0. And how do we solve problems where we have a polynomial equal to 0? Well, we factor the polynomial. So I'm going to pull that t out. And in fact, looking at it, this is probably going to be easier if I go ahead and pull a 12 out. And then I set both factors equal to 0. So we get 12t equals 0, or t squared minus 4 equals 0. Right? We divide both sides by 12. And then we add 4 to both sides. Take the square root of both sides, which means you got to add a plus or minus. So it turns out there are 3 different moments where we had an instantaneous rate of change, or a instant moment of instantaneous motionlessness, and that is t equals 0, 2, and negative 2. Right? So all 3 of those are moments when we were instantaneously motionless. Right? B, we've already done most of the work for, right? Because we want the speed at 1 hour. So the other way to rephrase this is we want the absolute value of the velocity at 1 hour. Right? So we plug that in, we get the absolute value of 12 times 1 cubed minus 48 times 1, which gets us the absolute value of 12 minus 48, which is 36. Right? So our speed at 1 hour is 36. Right? Our velocity would be negative 36, right? We can see from right here, this is going to wind up being negative 36. But since the question asks for the speed, it wants the absolute value version. So our answer here is going to be positive 36. All right. Okay. So, right. A bullet is shot straight up from ground level at 100 meters per second, what is the maximum velocity of the bullet? What is the maximum height of the bullet? Right. So, because this is something going up into the air and then falling back down, that is generally something that happens because of gravity. So this is one of those motion under the influences of gravity problems that we talked about, right? So we know it's going to look something like this. Right, and so for the purposes of this problem, G is always going to be fixed, right? We need to pick which one we're going to use, but G is going to be one of two numbers. And then S naught and V naught are usually things that we're going to be trying to find out. Or they're going to be things we're given, right? So we need to look through our words here, right? And so the first thing that catches my eye is this phrase, from ground level, right? Motion under the influence of gravity tells us how far we are off the ground. So if it's telling me that when it was fired, when we start this simulation, it was at ground level, that tells me that S naught is 0 for this problem, right? Because S naught is supposed to be the initial height, the starting position, and if we start at ground level, then we are 0 meters, because that's the unit we use here, above the ground, right? And just this right here, also, this sentence is describing the beginning of the experiment. It's describing where we're starting at. And meters over second is giving us velocity. So we have 100 for our initial velocity. Right, and then if we want to go ahead and plug some numbers in, again, we're talking about meters in this problem. That was the units that were given to us. And we said before, up here, that gravity is going to be 9.8 if we're dealing in meters per second squared. So we can go ahead and put 9.8 t squared there. Right? So that is our position function. And this question is clearly asking about the velocity. So let's go ahead and find the velocity. Right? The velocity is going to be the derivative of the position function. Derivative of 0 is just 0. Derivative of a linear function is just the coefficient. And then we bring this 2 and we multiply it down here. Right, to cancel out with that 1/2, and this power goes down to 1. Right, so that's our velocity. And now we want to find where this velocity is maximum. Right, so this one we don't quite have the tools for yet, except for what we remember. Right, this is just a linear function. Right, and it's even in slope-intercept form. So I know that the intercept is up here at 100, and the slope is negative, so it's going to go like this. Right? I don't know what to scale is. I don't know any of my x values here, but I know that it's going to start up at 100, and then it's going to start getting less. Right? So if I look at this graph here, it's pretty clear where the maximum is going to be there at 100 at t equals 0. right? Technically, if I look at this whole function, it's going to go up here as well, but we don't generally allow ourselves to go backwards in time and measure how fast a bullet is going before I shoot it. So for a problem like this, it doesn't really make sense to have negative t's. So the maximum velocity is going to happen at t equals 0. Right? Now, the maximum height, right, we can get that two ways, but we're going to talk about the calculus way to get that because it's a calculus class. Right? So this is v of t. So s of t looks something like this. Right? Again, I don't know where the scale is. I know that the origin starts there, but I have no idea where anything else is. But I know it's a quadratic, and it's a quadratic that opens down. So it looks something like this. So what I really want to do is figure out this. Right? And one of the things you might notice about that line that I drew there is, at least insofar as I have the drawing skill to do that, that's a straight line. That's a flat line. Right? And it's the tangent line at that maximum. So we're going to talk a whole lot more about using derivatives to find maxes and mins and all that. But for now, in this particular situation, it's even simpler than usual, which is that when the velocity is 0, and there will only be one time when the velocity is 0, then it's talking about a flat tangent line, and that's going to be the one maximum height. Right? So maximum height is always going to, for these motion under the influence of gravity problems, be where the velocity is equal to 0. Right, so we have our velocity function, 100 minus 9.8t. We want to know when that equals 0. Well, that becomes 100 equals 9.8t, and that becomes t equals 100 divided by 9.8, which, according to my calculator, is something like 10.241, right? So, there we go. We've gotten our, well, no, we haven't quite done it yet. We found the maximum velocity, right? And here we've just found when we reach max height. Right? So if we actually want max height, so this should be when we reach again. So height is actually given as the outputs of S, right? For all of these motion under the influence of gravity problems, S tells you how high something is. Anytime you see the letter S, it's talking about how high something is. So what we really want to find is S of 10.2041, right? Which this, I'll be honest, when I was preparing, I forgot to plug this into my calculator. But this is going to be 100 times 10.2041 minus 4.9 times 10.2041 squared. So this is going to be 1020.41 minus, oh God, whatever that number is. So I'm going to leave y'all to plug that into your calculator if you like, and get a final answer for it. I thought I could be clever and get part of it, but this would be the actual height. Whatever that number is, that's going to be the height. T is always going to be a time value. S is always going to give you height values, right? So since the problem asks specifically for what is the maximum height, not when do we reach the maximum height, we do need to plug it into S there. So one more problem here. Well, at least one more problem here. So if we drop a box from 50 meters off the ground, what is its velocity when it hits the ground? So this is another motion under the influence of gravity, right? Something is being pulled towards the ground, and that's what gravity does. So this is going to be another S of t equals S naught plus V naught t minus 1/2 gt squared. In this case, we're starting our experiment 50 meters off the ground, right? So that tells us that our starting position, our initial height, is 50, right? And at first glance, it doesn't look like we're given a velocity, right? So this is one where we have to sort of interpret the wording of the problem. Generally, when you imagine dropping something, you're just letting go of it, right? We didn't throw something out the window. We didn't toss it down. We didn't put any force behind it. We just held it out there and we let go, right? So that means that our initial velocity is nothing. Right, so we have as our position function this, and the question asks, what is the velocity? So we are going to want the velocity here. It's going to be the derivative of the position function. 50 becomes 0. We pull that down, and we get negative gt, so it's just negative gt. And in fact, we're talking about meters again, right? The only measurement was given in meters, so we know it's negative 9.8 t. So, now the problem is that usually, if we want to know what the velocity is, we have to know when we're talking about, right? And in this case, we do know when we're talking about, but specifically we need to know what t that is, right? So in order to get a velocity from our velocity function, we have to have an input, which means we need to have a time, which we need to know when it hits the ground, right? So when it hits the ground is the same thing as when S of t equals 0, so we need to solve that. Right, so S of t equals 0. I'm going to go ahead and translate that over to our 9.8 again. Right, so 50 divided by 4.9. Yeah. Equals, yeah. It is actually going to equal that 10.2041 again. And that's equal to t squared. So t is equal to plus or minus the square root of 10.2041, which is plus or minus, turns out I didn't actually estimate that, which is good because I'm not on the last step. Right? So we've got a little bit of a problem here in that we have two t's, but it's not really a big problem because remember what I said before, we're not actually in the business of time traveling to figure out whether something hit the ground before we dropped it out of the window. So the one we care about is actually just the positive square root. So that means that the answer to the question is v of the square root of 10.2041, which is negative 9.8 times the square root of 10.2041, which is roughly negative 31.305. Right. So that's going to be the velocity when we hit the ground. So one thing I wanna comment on here real quick. I personally don't care too much about units because I'm a mathematician and I never deal in units. It is very important to notice for derivatives, though, that you pick up a unit from both the df and the dx, right? So remember, v of t equals the derivative of s of t, which if we write it in Leibniz notation, that's ds dt, right? So the units of velocity are always going to be the units of s divided by the units of t, right? So fortunately here we didn't define a unit for t. So let's say t in seconds, because technically we sort of did when we used 9.8, right? Remember I said before, right, g equals 9.8 meters per second squared. So you can't use 9.8 unless t is in seconds. So since ds is in meters, since s is in meters and t is in seconds, then velocity is going to be meters per second. Right? Up here when we were doing this problem, right here, velocity equals ds dt, so velocity is in kilometers, because that's what s is measuring, per hour, because that's what t is measuring. Right? So whenever you're doing a derivative, even if it's not a position function, the derivative have units based both on the unit of the function and the unit of the variable. And they match up together the same way the differentials do, right? The same way the Leibniz notation does. So that's very important when you use this in other classes. And there will be a couple questions where I do ask you to be careful about it, because a lot of you are going to need to be careful about it when you actually use this stuff. Right. So another thing that we can do that I want to get some practice in, but I'm going to make a little bit of space for us using the trickery of digital nonsense. Just a little bit more space. I'll try to make it work. So a ball tossed up from 6 feet off the ground, hits the ground 10 seconds later. Right? So let's ask, what is V naught? Right? So I wanted to do a problem like this because in our past two motion under the influence of gravity problems, we started off with an S naught and a V naught, and we had to find some other things. Right? But it turns out that if we start off with those other things, we could also find S naught or V naught. Right? So we know that S of t equals S naught which is the one that we're given, so 6, plus v naught, we don't know what it is. We weren't told anything, right? We were told that we toss the ball up, which indicates that we're not starting with velocity 0, right? Last problem, if this said we dropped a ball from 6 feet off the ground, we know what the initial velocity is. It's 0, right? But the fact that it said it was tossed up, that indicates that it has some velocity along with it. Minus 1/2, and I'm going to go ahead and fill in the 32, since we know we're talking about feet per second squared. Right? So this is 6 plus the thing that we don't know times t minus 16t squared. Right, so now we have to think about what we do know, and the thing that we do know that we didn't learn other times was that it hit the ground after 10 seconds. Right, now we talked before in our previous problem that hitting the ground means that the position function equals 0. So what this sentence is really telling us is that when we plug 10 in for t, right, because 10 is measuring the time there, we get 0 out of the position function because that's when it hits the ground. Right, so this is equal to 6 plus v naught times 10 plus, minus 16 times 10 squared. So we do some algebra, we get 16 times, what's that going to be? 4 zeros? Yeah. Minus 6 equals v naught times 10. So this is 1,59994 equals v naught 10. I feel like something went wrong here. Oh, I see what it was. I just got too excited about all my zeros, and I squared 10 twice. That's not helpful. So we have 16 with 2 zeros minus 6 equals v naught 10. So this is 1,594. So v naught itself we get by dividing by 10, which just lets us move the decimal point over. So we get 159.4. And again, we recall this is a velocity. So it is the units of s divided by the units of t. So our initial velocity was 159.4 feet per second. So it turns out doing word problems takes a lot more room on the canvas than most problems do. But we got a good number of word problems here. Our next couple sections are, well, one of them is going to be, the next one's going to be fairly short because we're going to talk about higher derivatives. And it turns out that just means take the derivative more times. And then we're going to go back to learning a couple more rules for our next couple sections. So I'll see y'all next time.